Greetings to the panels, Dr. Norizan and Dr. Fadiha, my supervisor, Dr. Liu Fun, and to everyone else. This is my presentation for FYP 501 on my topic, MIMO radar antenna. My name is Yong Jourdan with metric number 191392563. So as we begin, let's start with what are MIMO radar antennas, with the basic concepts and their operations. So first, let's talk about MIMO. Well, MIMO is just basically multiple transmitters and multiple receiver, multiple input, multiple output, MIMO. So multiple inputs and outputs working simultaneously. So you get in the concept there are multiple different antennas. So in this specific type, you'll be multiple different radars. So let's talk about the radars. So we got the radar classifications. There are three main radar classifications: short-range radar, medium-range radar, and long-range radar. Each with their own different detection range, their own beam width. So like the further the range is, the smaller the beam, the narrower the beam width would be in front. So combine that together with this MIMO system, we're going to get multiple radars with multiple beam widths scanning at different areas. Well, this is different from an array antenna, as in an array antenna with multiple elements combined together with a single input. They're just going to have beams protruding in different locations and different angles. But with MIMO radar antenna, you have different outputs with different inputs. So look at the advantages compared to the others. So high tolerance for hiatus in target detection. So like as the target moves away, it's further, or there's a gap between the hiatus in the target detection, right? As long as one radar isn't able to pick up, the other radars might be able to pick up the target. And then it works better at high signal to noise ratio compared to array antennas. This is true also, as in you have more sample sets to get the data from, rather from array radars where they only have one input and one output. So like you have more sample sets which you can compare. And then the exploitation of spatial diversity to overcome target fading, which is same as earlier said. You don't have only one output, you have multiple outputs where you can correlate the data together to get an accurate result of what has been received. These are the main advantages of a MIMO radar antenna. So as we go on, let's talk about the problem statement, objectives, and the scope of limitations. So the problem statement for my project is to obtain the optimal sparse distance between adjacent antennas. As in like EM theory, when you have two transmitters placed at like quite close to each other, they might interfere with each other's signals, thus causing maybe interference. So to obtain the best distance in between adjacent antennas. Next, we would like to have a balance between wider aperture and longer range. So we would like to have a radar which is able to scan a wider area, however, while not having the drawback of being too short or in a medium range. And then usually this kind of radar components, they are fabricated using high quality substrates, which are like Rogers Duroid or Taconic, because due to its very, very low dielectric density. And lastly, they require machines of high precision to fabricate or mass produce, as in the shapes of those that are very, very small and precise, so they require machines to fabricate. So my objective of my FYP is first to create an optimal sparse array, MIMO radar antenna, so like an array with MIMO. So I can use the best of both worlds, the advantage of both worlds, MIMO's multiple sample sets with arrays, a wider range and aperture. Next, we'll talk about the balance between wider aperture and longer range. So can we have optimal usage in multiple different applications? So I wouldn't be limited to just one application of radar. The radar could be used and applied in many other different things, such as automobiles, drones, moving machines, or maybe even household items. And lastly, accessibility. So I would like to make this radar accessible, easy to be fabricated and mass produced so that it could be applied into, as earlier said earlier, different multiple appliances or things. So this goes under my limitations is I like to use patch antenna so that, well, it doesn't require that high of precision compared to a smaller circular antenna. Compact size, it's small, so it could be applied in multiple different applications without taking up too much space or giving up too much weight, and the ease of fabrication. Well, for this case, currently we're trying to use the FR4 material so that it could reduce and save in costs and easily produced. Well, the abundancy of that. So now we're done with the introduction, we'll go on with the preliminary research, the literature review. The literature review, I focused on four main parts, which are the antenna substrate, the feeding techniques of the antenna, the radar frequencies, and the MIMO radar antennas. Well, as you know, there's the antenna, the microstrip antenna is usually printed above on the substrate. So the dielectric substrate is very important in terms of trying to get your desired beamwidth or results or reflection coefficients, all that. So without, let's move into antenna substrate comparison. So this reactive comparison compare between four different substrates which are more widely used, which is FR4, Arlon, AD300C, Rogers R0, 4003C, and Mica. So out of all those, Mica has the highest electric absorption, and then with the smallest loss tangent. So ER is the dielectric constant, and then 10 is the loss tangent. Yeah, and the bandwidth, return loss, and gain. So generally, we could see that FR4 is in the mid-range for the gain, which is 4.89 dBi compared to the highest, which is 7.5 with Arlon. Arlon is able to achieve a very high gain due to its very small dielectric constant at 2.98. However, its drawback is it is that its loss tangent isn't as small as Mica. However, it got relatively smaller loss tangent compared to FR4 and Rogers, so it's able to obtain a very good return loss and bandwidth. So best of all worlds. Rogers R0 4003 in other hand also works fairly well, with a high gain compared to FR4 and Mica. Over Mica, as good as the loss tangent is a very high dielectric density. So the constant very high is unable to obtain very good results. Smaller bandwidth and somewhat okay return loss. Moving on, we'll talk about the antenna feeding techniques. First one, we have the microstrip feed, which is on the top left. Yeah. And then the top right is by coaxial feed. Then the bottom left is the aperture coupled feed. And the middle is the proximity coupled feed. And the last one is coplanar wavelength. So antenna feed, they are generally spaced into two different types. The first type being contacting feeds, and the second as the non-contacting. So contacting means as in the feed is directly connected to the patch itself. And the non-contacting is through radiation, it's not directly connected. So you can see at the top left, directly connected to the patch using a microstrip feed, and the top right directly connected below using the coaxial cable feed. However, for aperture and proximity, there is no direct contact between the signal source, the feed, and the patch itself. So there's a distance in between aperture, there's a hole in between them, so the radiation good. And then there is for the proximity, there's radiation, how there's no aperture, so it's like two plates between each other. Lastly, coplanar waveguide, where everything is on one plane, which is the ground panel, the patch, is all on one plane with the substrate below. So to compare all different techniques, you could see that it's looking at terms of spurious field radiation, which is radiation of adjacent frequencies, reliability, ease of fabrication, impedance matching, and bandwidth achieved. So for spurious field radiation, the coplanar waveguide feed has the lowest, less spurious field, as the ground is directly next to the patch itself, so it's able to absorb most of the spurious field. The reliability, however, the best is that microstrip feed line. So because it's directly connected, you wouldn't have the issues of it not being connect or the dielectric constant stuff and all that, or because it's directly connected. So the dielectric wouldn't have that much of a difference in causing the signal to achieve or not be able to achieve. The ease of fabrication, again, microstrip line is easier. It's because everything is together in the same plane, and then it's just like that. You don't have to design the ground itself on top of the plane, which is easier to cut off. Impedance matching is easy for all of them, as in now currently standard we're using with 50 ohms. And the bandwidth achieved is the highest that proximity coupled feed, as they're not directly connected to each other, plus the radiation is could be able to expand water, and you have a larger bandwidth. After that, we look at radar frequencies. So there is actually no limit to what radar frequencies are. Typically, it starts from the radio frequency, which is 10 to the power 6, all the way until visible light, which could be used as radar frequency. However, as you increase in frequency, you increase in wavelength. You decrease in wavelength. So the shorter the wavelength is, the shorter the range of the radar would be. So they will have multiple different parameters to consider, such as the physical size of the antenna, transmitter power and beam width, and the atmospheric attenuation. So first, talk about physical size. Well, the larger the wavelength, the larger the transmitter has to be. So at low frequency applications, the waveguides or the patch itself will be huge compared to higher frequencies where the patch will be very small. The transmitter power and beam width. So the frequency that you choose indirectly influence the ability of radar to transmit large amounts of power. All this is due to it having to concentrate the power in one direction. Typically, larger wavelengths, you would have a larger aperture, and it's easier for you to transmit compared to smaller wavelengths, which is weaker. To talk about this, then atmospheric attenuation, where as the electromagnetic signal is transmitted within free space in the atmosphere, there might be absorption due to water vapor and oxygen, thus making the signal weaker. We can look at the relationship in the graph over here. So as the frequency increases, you see the attenuation is a lot higher for higher frequencies. So there are limitations as we are using very high frequencies, such as the automotive radar, 77 gigahertz. Well, when it starts to rain, you will have disruption and you will have weaker radar sensing capabilities. So you will rely on other radar systems such as LiDAR instead of just electromagnetic waves. So now we look at the MIMO antennas, which currently they have done. So you can see on the bottom left, that is a whole phase array antenna, which is multiple, they call it the comb antenna. And then the middle one, you'll have the C MIMO antenna, which is patched. And the last one, which is the fan-shaped array antenna. So generally, all these are different designs of MIMO antennas, which is to obtain the same thing, to be having multiple input and multiple output. Then look at the MIMO radar specifications: antenna polarization, radiation efficiency, and antenna gain. Polarization is to see whether it's on the E field or H field, or it's circularly polarized. Usually circularly polarized would be better for some applications, as in let's just say in a drone setting where one would have different elevation and angles, so you require circular polarization to connect. Otherwise, they have a very major drop in the signal received. radiation efficiency, so how good does it radiate, and lastly antenna gain, which is directly just saying that in a direction, how strong could the antenna or thing could concentrate or propagate. Well, that is it for our basic about the literature review. So move on to the methodology. So for the methodology, we'll have the using the formula of the patch antenna, which is general formula, where we use to calculate the width and length of the patch antenna itself on the substrate using FR4. We will have an issue, however, at high frequency applications where the feed line, you can see here, the thick yellow one, is larger than the patch itself. So this is because of the fact that we have a thick substrate, and then the feed has to be in a given ratio with the substrate, so it makes that big. To overcome that, well, we design an SMA connector, which is the standard one with the legs connected directly to the board of the FR4. Thus, we don't have to create such a huge feed to overcome that problem. So now we're talking about the single antenna radar. Antenna design is such as this. After we use the calculations to achieve the dimensions, and then we have successfully achieved the reflection coefficient of negative 35.75 dB at 24 gigahertz, and the radiation patterns such as this in the 3D field, in the 2D field, and here back in 3D, yeah. Okay, so we got a decent single patch antenna. Now we'll try to make it into a MIMO version. So it will be split, and then now we try to doing a 2x2 MIMO radar antenna. So we have one side 2 ports and then 2 arrays, so 2x2. The design is somewhat like this. However, we have achieved a reflection coefficient at 2 different spots. One is at 22.823 gigahertz at negative 12.85 dB, and 26.04 gigahertz with negative 17.622 dB. You could see this is somewhat dual band, and the far field monitor, a gain of 3.75 dBi and efficiency of 60.37, which is it's the same for both ports, so it's just vice versa here. And then here is the radiation pattern. You can see it's highly directive, but it's not in a wide aperture or a good distance. So the takeaways and improvements to be made for my MIMO radar antenna. From the far field monitor, we could see earlier in the MIMO antenna over here, you see that the radiation pattern isn't as good as I hoped for, because I would like to have a singular beam width and some smaller side lobes, to be concentrated, because it's radar, you have to make it directive. Yeah. So the issue might be with the single radar design. So we'll have to change the design to obtain a more directive version. Then we'll improve the signal. Second, implementation of the array antenna design as shown in the over here, the COM array. So we have the advantages of both an array antenna and a MIMO antenna, which is more reliable and you can use beam width, beamforming. And lastly, the increment of number of inputs and outputs. So we're not going to stick with 2x2, maybe you're going to do with 8x8. So 8 inputs and 8 ports, or 8 arrays. So this, we could improve the spatial diversity and all this. However, this would just all start with the improvement on the single radar antenna design. Well, this concludes my FYP1 presentation. If there are any questions, you could contact me with the contact details shown on the screen. And thank you all very much. Thank you.